talk is on towards general purpose program obfuscation via local mixing, and the authors are Ron Kennedy, Claudio Chaman, Eduardo Mucciolo, and Andre Rockenstein, and Ron is giving the talk.
Thank you. Yeah. Thank you very much. Okay, let's see if this works. Okay, so indistinguishability obfuscation is an interesting, intriguing beast, as we know. So, and it carries no computational hardness by itself. It exists even if P is equal to NP. But we know that with a little bit of hardness, it enables amplifying and molding this hardness in many ways. In particular, just assuming that P is not equal to NP plus IO give us 60% of crypto, and we add some more assumptions to get the rest of crypto essentially. So it's really a pretty amazing beast. On the other hand, constructing IO, it's a challenge. As we know, we've just seen for the last talk, those constructions that do it are really amazing feats. But it's really complex, right? It's highly structured primitives, high overhead, and it's complex. You can say maybe roundabout, we don't know. So the question is, can IO be constructed kind of from first principles, keeping that it's so simple to begin with, maybe. So this is the topic of this work, is really to try to make a stab at a first principle approach. We're not far from being there of course, but hopefully to be able to convince you that it's interesting enough to further investigate. So what is the basic idea? So it's like as simple as it gets. So what's going on here? Okay. So we have a circuit, right? And we want to obfuscate or re-randomize it. So why not just do it in small steps? So we pick, let's pick a small constant side contiguous segment of this circuit. Write down its truth table. It's exponential in size, but never mind, it's constant. We're gonna choose a random other implementation of that same truth table. Maybe it's doubly exponential, but still the constant. And we're going to write it down instead. We're going to replace this, what's happening here? It's stuck. Oh. Okay, just slow. So we're replacing it with another implementation of that same piece. Now it was so much fun, so let's do it again. We pick another piece, we randomize it, it's implementation, and right there, we put another piece, and see what's going on here. There's some overlap, so this confusion diffuses a bit, and we just do it again, and again, and again, and again. And the question is, what's happening now? What do we get in the end? So, clearly, the functionality is preserved, that's how we constructed it. But what about security? So the intuition or the hope is that these local perturbations will create some global effect. But so what will this effect be? So the first naive idea, hope, would be that we show that this process converges to some stationary distribution that depends only on the truth table of the original circuit. That would be great, that would be awesome. But that's probably too much to hope for, because this would imply that NP equals co-NP. Goldwasser and Roblum showed us, in fact, even just the mere existence of this polynomial-sized path of local perturbations between every two functionally equivalent circuits will already imply that NP is equal to co-NP. So it's probably too much to hope for, right? But if you look more into the process, there are actually more concrete reasons why this cannot work by itself. So first, in order to provide meaningful re-randomizations of short circuit segments, we're going to have the new circuit be slightly larger than the old one, because maybe there's only a few or couple, or even one possible circuit that implements that particular truth table with that size. So the circuit is going to grow, which by itself maybe is not too bad because we only do it polynomially many times, but this means that there is no hope of reaching a stationary distribution, right? And furthermore, this randomness that we put in is clustered like in small places, so it's maybe easy to detect and reverse, etc. So by itself it's not going to work. We need some more structure here. So what is the structure that we're going to go for? So surprisingly enough, or maybe not surprisingly, we're going to go to reversible circuits. So let's remind ourselves what's reversible circuits from quantum or whatever other classes that we took. So a reversible circuit is essentially a sequence of gates, which each gate is reversible or it's a permutation on the n-bit state. And the permutations are simple, so only touch depend on three wires or bit values. In fact, it's just one bit value, x7 here, is XORed with a Boolean function of the other two wires, right? And in particular, you write the same gate twice, it cancels itself out. Each gate is the inverse of itself. And so a circuit is a sequence of such gates, so it's a permutation, even permutation even. And you can write down the permutation. And we know furthermore that we can embed standard circuits within reversible circuits, and we can even do it in a way that is kind of I/O friendly. So in particular, it's sufficient to consider I/O for reversible circuits. Okay, so it's sufficient, but why does it help? So I'll give you some reasons, right? We'll see along the way. So first, just on first principles, so the reversible model gives kind of less protections to the programmer. It should be easier to obfuscate. So information is never lost, it's never duplicated, there's no fan-out, and all internal states are always visible from the output. Computable from the output. So that's one. But there are much better reasons. So this model of reversible circuits lends itself very nicely to the notion of a random circuit, random reversible circuit. You just choose each gate randomly. There's polynomially many gates, like n cubed, order of n cubed many gates. So you choose them at random every time, so you have a random circuits. And unlike standard circuits, if here when you choose a random circuit actually is meaningful. In a standard model, a random circuit would most probably compute a stupid function like a 0 or 1 function, but here it does not. So there are some very nice properties, but let me try to go through them one by one. It's actually lent itself to what we're doing. So the first thing is that not only is the functionality of a random reversible circuit meaningful, not a 0 or 1, it's actually was proven to be almost chaos independent, even for a relatively small number of gates. So in particular, so there's a whole list of works that starting from Gowers and very recently a lot of new interest in this problem is showing that so you can make a random reversible circuit of m gates is actually almost k-wise independent for some k, which is polynomial fraction of m, this is for any m, and furthermore, it's been conjectured that this not only is it k-wise independent, is actually pseudo-random. And furthermore, if you think a little bit, you see that this is essentially the quintessential block cipher, a random reversible circuit, and essentially any other block cipher, AES or whatever, is kind of a knockoff of this quintessential block cipher. But never mind, that's a side issue. Okay, and so far it was about the functionality of these as black box access, but actually I argue that actually when you get white box access, you actually see the circuit itself, it has some very nice pseudo-randomness properties, which is very nice in this random structure, random function confluence. So let me say what I'm being more explicit. Here's an assumption that we make in the paper. So start with a circuit. You're giving a circuit, some circuit, and I only use this circuit as the function to determine the permutation computed by the circuit, right? And here are two different distributions over circuits that compute that particular permutation. One is I got a circuit of m gates. Now I'm giving you many more gates, like m times mu security parameter gates. And I'm choosing at random a circuit out of all circuits of that number of gates that compute that particular permutation. That's distribution number one. Distribution number two, I again give you a circuit that computes that permutation, the same number of gates, but I choose it differently. The first, some mu gates, security parameter gates, I choose completely at random, irrespective of everything. And then the rest, I sample, at random conditionally of getting the permutation that I want, right? So neither of these processes is efficient, but never mind. And I argue that you will not be able, in polynomial time, to distinguish between those two distributions. Oh, whoa, okay. So anyway, so this is an assumption that we're making. Okay, so a third reason, which is actually very pertinent to us, is this randomization process actually looks very nice when you look at the random reversible circuits. So every time you take a segment to randomize, actually take the entire state. And furthermore, when you do this nice process, what you get is that the reversibility actually have some information about the circuit be effectively erased. And also, you get the random walk on this Kelly graph of a symmetric group, the alternating group. And actually, we have some understanding of this random walks, which allow us to do things. And the growth of the number of circuits that you have for a particular functionality in the number of gates actually is relatively well understood. So we can actually, inflate the circuit up to some point, and then know, okay, now it's, we injected enough, extra gates in this, and now we no longer need to keep extending the size, and we just keep re-randomizing. So we injected fat, and now we're kind of churning the fat around. So we have a potential to get, or we will get some stationary distribution. The question is how fast and how, what does distribution look like, which is something to analyze. We haven't analyzed that yet, unfortunately. But let me actually show you how you get from obfuscating short random circuits to obfuscating all circuits, right? So we define the notion of what it means to obfuscate random circuits. I don't have time to show you. It's in the paper. But now let's just say how we get from random circuits, from obfuscating random circuits to obfuscating every circuit. So here's like in a minute how to do it. So you're giving an obfuscator for random circuits. So the first thing you do, you generate a random identity circuit. So M-gate circuits, which are pseudo-random, except that they compute the identity permutation. How do I do that? I choose a random circuit. I obfuscate it. I obfuscate it again. I take the two obfuscated copies. I write them next to each other, one in reverse. So they together they compute the identity permutation. And they look random. And now once I do that, I can actually extend it to have like random M-gate blocks that compute individual gates. How do I do that? Well, just rejection sampling, right? So I pick random identities until I get one, which is the first gate is the gate that I want, and then I throw out the gate and the rest is compute the same gate, so I'm good. And now, how do I obfuscate the entire circuit? I first take each gate and I write this gate as a random block of that functionality. I write them all next to each other. Now, locally, they're random, but of course, it's not obfuscated because there are seams between the blocks that actually compute the original circuit. So all I need to do now is hide the seams or solder individual blocks. So what do? I take like a little bit of gates from the left, a little bit of gates from the right. Together, it's random because it's just portion of the overall, each portion. And then I re-obfuscate that part. And here's what I get in the end. So that's it. And we show that this is IO under this SCP assumption. So very simple. And then we have this candidate obfuscator, which I wanted to tell you, but I told you the principle before. And there are of course, a lot more open questions here, but I think I'm out of time. So thank you.
Maybe one very quick question. Yes.
So, Ron, why did you, at the beginning you said, at the beginning you said we're not quite there, but it sounds like you do have an I/O construction based on this SCP assumption, or?
Well, it's based on this SCP assumption and the ability to obfuscate random reversible gates, and this is this conjecture thing that we just have to analyze this random process, right? So it's yeah.
Thanks.
But once we are there, we do have something, yeah.
Okay, let's thank Ron again.